So as you said, I will talk about efficient navigation of microswimmers in turbulence. And this is work that started in my postdoc in Rome and work done in collaborations with many former students and collaborators. But today I will mainly introduce the problem in a broader perspective and introduce the tools we use to analyze these systems and maybe not go into so much detail on all the results we have found. But I will introduce them as well, but only briefly. Okay, so the plankton navigation problem is a quite complicated problem. So if you are a small plankton, like a zooplankton here, your aim is to navigate some flow structures, some turbulent flow, in order to find your food source and hopefully avoid dangerous predators. And this is a complicated problem because you can't navigate using a map like us humans. So the flow is ever changing. So you always need to take into account that the flow changes. So you can't really rely on that some place that were good yesterday will be good tomorrow or something like that. So you always need to adapt to an ever-changing environment. And nevertheless, plankton in nature are able to do this to some extent. And the main tasks are to obviously avoid predators. So if you are eaten, you are game over. So that's maybe the main drivings of the plankton strategies. But you must also avoid dangerous flow regions. So these could be regions where the signals from a predator get masked by the surrounding flow, so it's hard to detect predators. Or it could be very high turbulent regions where your body gets deformed and tears apart. Or it could be downwelling regions where the ocean currents take you down to the depths where you can't swim up again. So it's a very complicated or a hard problem for a small microswimmer to achieve all these tasks. Moreover, you need to track regions with much food and where you can find mates. So the ocean is in general vast, so very large areas where you don't have any mates, and then or food, and then regions where it's crowded. And another navigation task is daily vertical migration. So it turns out that the zooplankton every day at let's see here, sunrise, then they swim down to the depth of the ocean to avoid visual predators like a fish larva, and then in the dusk. No, in the evening they come up again, and being millimeter size, they can swim up to 100 meters, corresponding to up to 100,000 body lengths. And all this they must do while conserving energy. So plankton navigation in the ocean is obviously a very complicated problem, and it has been a long-standing question on how this is done. And our approach was to address this problem using machine learning. So the question is if we can use machine learning to find efficient navigation strategies, maybe not for everything, but at least for some selected navigation goals. Okay, so why should we care about plankton navigation? So first and foremost, it's the foundation of marine food chain and the carbon cycle. So you have phytoplankton and zooplankton. So these are the main sources of food for larger animals. If we were to remove these, essentially no life in the ocean would be possible. So they are the basis of the food chain in the ocean. And then it's important to understand how the plankton growth will change if we change the underlying flow structures. So, for example, the climate change is expected to change the turbulence levels and heat, temperature and so on. And then the question is what will happen with plankton populations at different places. And for example, we see already now that plankton production is increasing closer to the poles. And moreover, it's important for the carbon cycle. So phytoplankton corresponds to around 50% of the photosynthesis in the world. So they more or less produce as much oxygen as the land-living plants. And then during an eventful destiny after they die, some ratio of these will deposit on the ocean floor. So this could serve as a mean of carbon capture. So if we were to, for example, fertilize regions of the ocean, we could increase carbon capture and remove carbon from the atmosphere. But then to understand the mechanism, what will happen if we fertilize, we need to have a better model or better understanding of the plankton dynamics. So currently, very large areas of the ocean underperform and can get a much higher number of planktons. Okay, so that's one example. Another example why plankton navigation is important over plankton is important is that they affect the albedo of oceans and clouds. So the size and shape and abundance of different plankton will affect how much of incident light gets scattered back. And in particular, together with different flow structures, we can get some alignment behavior. So if you have a typical shear flow, elongated plankton will elongate, and that will reduce the incoming light. And then the question is how much will these reductions change if we change the turbulence intensities due to climate change and so on. And you can see here an illustration of two different species of plankton diatoms and coccolithophores. And you see that they significantly change the albedo or the color of the ocean surface, and that's significant for the radiation balance of Earth on a larger scale. Another example why plankton navigation is important is in aquaculture. So many fish larvae prefer certain species of plankton, or they need certain species of zooplankton in order to get the right fatty acids to grow in the best way. So if you try to feed them artificially, many of the fish larvae get some defects and deformations. So it's better to feed them with natural food, but it's hard to cultivate zooplankton on a larger scale. So it's important to understand what makes them tick and what under which conditions the zooplankton will grow as much as possible to use them as fish food. And finally, in the future, we expect engineered microswimmers to be able to exist in the lab, and these have, well, uncountably applications. So you have delivery of medicines in the body, or microsurgery, or mixing of molecules. So you can well, mix chemicals or medicines, or you can clean up biohazards or oil spills and so on, or you can use such smart engineered swimmers to change the rheological properties of a flow and so on. So the applications are endless once the experimentalists manage to engineer artificial swimmers similar to the plankton in the experiments. Okay, so that was some motivation of why we want to study plankton navigation. So is there a question or? Okay.
Not for the time being.
Yeah.
No.
So just shout if there are any questions, and I will try to answer.
We will do, happily.
Yeah. Okay, so now if we look at how plankton can navigate in the ocean, the first and most obvious perhaps way is to swim, and this is mainly done by zooplankton, but also some phytoplankton like this flagellate does this. So it uses a flagella to swim, and in this particular example, it's mainly terns. Or you can use cilia, which is mainly smaller flagella, or a zooplankton that uses its appendages to swim, and there are many different swimming behaviors, and here is one more exotic, which is more like a pogo style swimming behavior where it has some appendage that it cyclically beat to do this swimming behavior. Another example is jumping behavior, and here is a fish larva, and these small are the zooplankton, and you see that they jump away, and one can see that they actually jump at a distance. So before the fish larva reaches the zooplankton, it jumps away, and this must be somehow mediated by flow disturbance in the flow. So the fish larva makes a disturbance, and the zooplankton jumps away at a distance. So that's the way these zooplankton or copepods escape predators. So I will maybe discuss this in more detail later, because this is something we have been working on. And a third example is plankton motility. So here are some diatoms that are slightly heavy, and by changing their size, they change their buoyancy, they can change the dynamics. So if you look at an individual trajectory or an individual cell, you see that it moves with a constant speed, and then it stops, and then it moves again. So that's by changing its buoyancy. So you can do this quite rapidly, of the order of less than 1 second, and then by doing this, it can, well, to some degree, it affects its motility where it goes in the flow, and it also disrupts the boundary layer around it to be able to sweep up more nutrients. So by doing this rapid change in the velocity, it can get more nutrients. And finally, the last example, or several examples, are that you can change size, shape. So, for example, by changing the shape, swimming plankton can change the relative position of the center of mass and the center of hydrodynamic action, which changes the dynamics. So by changing the shape, it goes from something that swims upwards on general, so this is bottom heavy, so it swims upwards, to something that instead turns and swims downwards on average. And this is done to avoid dangerous regions in the flow. So it turns out that half the population does this change in shape while exposed to intense turbulence. So half of the population goes up and the other half goes down, and the authors speculate that this is due to some some survival mechanism for the entire population, that half of them have the possibility to go up and get the sunlight, while the half of them play it safe and are able to go up at a later stage when the turbulence is less intense. They can use chemicals, for example, changing the releasing chemicals to change the rheological properties around them. They can form colonies. So it's similar to the Tour de France, where you have bicyclists after each other to change the drag. Small phytoplankton can attach to each other to form longer chains, and these change their swimming behavior. So if you have a single swimmer, it will on average typically. So all of these are bottom heavy, so they will tend to point upward, but due to dynamical interactions with the flow, they tend to move upward in downwelling regions where the actual flow goes down. While if they attach to each other like this and form an elongated particle, one can see that they instead still go up, but they go up in the upwelling regions. So by moving together in a colony or a column, they can increase their upward migration. Okay, so these are some examples on different motility strategies from plankton, and basically this is to show you how many different possibilities there are. And in what follows, I will focus on swimming, and in particular, I will focus on swimming copepods, which are one of the larger plankton species. So these are zooplankton, and they are quite strong swimmers, and they have quite good sensing abilities. So they should be able to navigate turbulence in different ways. And this is also what is seen in experiments. So one can see that the copepods adapt to underlying flow. So here is an example where it's shown that copepods on average swim against the flow. It's not entirely known why this is done, but the hypothesis is that if they swim against the flow, they can maintain their absolute position in the ocean or in the flow current while encountering large fresh water content or what you say, flow. So you get fresh flow with lots of hopefully food. And what's shown here is the flow speed. So this is the Z direction. So at 0, it's close to 0. So I don't know why there's some timer in my presentation, but that's not. And then at larger values of Z, the flow is larger. So when it's here, it moves to the right, and here it stays at a position if it doesn't swim. And then the copepods turn out to swim against the flow, so it has a larger swimming to the left direction when the flow speed is large, and the net effect that is basically stay at a fixed position. And it's unclear how this is done in nature. I mean, you have some Galilean invariance, so in principle you shouldn't be able to measure the flow speed. So it's an open question how this is done by copepods in nature. Another example how they adapt to the underlying flow is by swimming in spiral around vortices. So without the flow, they more or less move in random directions, while if you have a steady vortex of typical characteristics as the turbulent vortices in the ocean, they tend to move in spirals inward to the vortex core, and this is also open question why they do this. A further example how they adapt to the underlying flow is anomalous diffusion in turbulence. So I will not go into the details, but basically what one sees that if you have intense turbulence, the dynamics is more or less diffusive, while if the intensity of the turbulence is larger than 0, but not very large, the copepods can adapt the dynamics to move away quicker in some direction compared to just moving randomly, that is diffusion, or the case where you have an intense turbulence. And one also observed that copepods can sync the jumping velocity to the flow scales in turbulence to increase their displacement. But also here, many questions remain. It's very unclear how this is done, but it turns out that they can use turbulence to facilitate their movement in some direction.
Kristian?
Okay. Yes.
Can I ask you a quick question about the first point that you raised here? So you mentioned that the plankton shouldn't be able to sense the underlying flow. Is that because are there some global properties that they shouldn't be able to sense locally? Why shouldn't that be possible?
Yes, so the problem is, so they can measure flow gradients, but they can't measure the actual velocity, because if you are a plankton and you have a uniform velocity to the right, you will just move together with the flow. So you can't see that there is a flow if it's a uniform. So somehow there must be some gradients that they can use, but it's unclear how this is done.
Okay, that absolutely makes sense. Thanks very much.
Okay. Yeah. Any more questions so far?
I don't see any in the chat. So let's continue. And whenever there are other people posting in the chat, or if they start unmuting themselves, they are happy to do, they're welcome to do so.
Okay. Yeah. So we see that they can adapt to the underlying flow, and the question now is, how can they do this? And I will not go into the details. I don't know all the details, but basically they have chemical and mechanical sensors along their antenna and body. So if you look at the copepod, you see these hair-like structures, and basically these will bend depending on the flow at this position, and that would help you navigate. And then you also have chemical cues, but I will not discuss that too much. That's the dominant signal if you're not in a turbulent environment, but when it's turbulent, it's most likely easier to navigate using mechanical sensors. And basically how they can do it is by having these setae, or these hair-like structures at different locations. So without the flow, you just have a neutral orientation of these setae, and then if you have a strain, that is a flow that moves in to some region and then out perpendicular, you will have some specific pattern of these setae. So you will get stretch where the flow moves out, and then they bend inwards when the flow moves in. And if you have a slip velocity, so that's the difference between the flow velocity and the velocity of the copepod, then you will have a different pattern of these setae. So you can imagine you move to the right, and then these setae bands. So that's related to the question earlier. So they can measure the slip velocity, the difference between their own velocity and the flow velocity, but they can't measure the flow velocity by itself. And similar, they can measure the angular slip velocity, that is the difference between their own rotation and the flow rotation. So these are the typical linear flow configurations that they can detect, but they can also, since they have an array of these, they can also detect more details about nearby objects. So for example, they can determine the size and velocity of a close by particle that settles or moves through the flow in its vicinity. And so they are quite capable in sensing the flow environment in this way. Okay. So that was some overview of how plankton navigate, and so some points on what they do. Now, coming back to the question, can we use machine learning to find strategies for such plankton? Then we started with my Rome postdoc to use or address this problem using something called reinforcement learning. So this is a means of machine learning where basically you do trial and error, similar to how human learns. So the typical setup is that you have some state, so that's a measurement of the environment, and then we have the agent. In our case, that's the copepod, and this can take actions, and that's different swimming behaviors. So it could swim straight ahead, or swim with the turning, or whatever the copepod can do, that it can actively adjust. And then it interacts with the environment, and after this interaction, we give it a reward. So depending on how it performs in the environment, we can get a positive or negative reward. And this reward is used to update a policy. So that is a policy how we should change the action given the state. And in reinforcement learning, we can optimize these rewards, we can produce a navigation strategy where we maximize the long-term reward that this copperpod or this agent receives. So this is important that it's long-term, so you can do suboptimal actions in the short run, and in the long run, that will lead to a better performance in the long run. So that's quite essential in this reinforcement learning. So you don't just do a short-sighted optimization. It's really optimizing a long-term goal. And in what follows, I will make some examples to make this much more explicit. So this was just the outline of reinforcement learning, and now I will try to explain how it works in more detail. But to do this, I have an example here, which is to swim against the flow. We have this copperpod here, and then we have a nutrient concentration here, we say, and then in between there is a counterflow, and the copperpod maybe it can measure some chemical concentrations, and the question is, should it spend energy to move to the right depending on the signal? And we make a very simplified model of this by dividing the space in 4 states. So we have 4 flow regions like this, and then the actions the copperpod can take is either move one state to the right or move one state to the left. So you can move from 1 to 2 and 2 to 3 or 3 to 2, so to nearby state. And then we assign some rewards, and we say that if it moves to the left, that's 0 reward, so it just follows the flow to the left. It doesn't need to spend any energy. If it moves to the right one state from 1 to 2 or from 2 to 3, we get the -1 reward. So that's a penalty because it needs to spend energy to swim against the flow. And then we add a high bonus if it moves to state 4 where all the nutrients are. And to keep track on what the agent or the copperpod learns, we use something called a Q table. So that's used to store the experience that this copperpod accumulates by trial and error. Okay, so now if we apply the reinforcement learning scheme on the first page, okay, so I should just say that this is one way Q table. This is something called Q learning. So that's one way of reinforcement learning that we have used a lot because you can see what the strategy is, but there are also other options where you have neural networks instead of a table and so on, or well, other methods for reinforcement learning, but I will focus on this one because that's quite easy to understand what the agent actually learns. Okay, so now going on to the scheme, we start by measuring the state. So if we start at the left-hand side here, we are in state 1, and then we need to take an action. And one way, or since the Q table should somehow encode how well or how good it is to take an action in a given state, we use something called a greedy action. So that's the currently best action, the action that we think is best at the moment. So that's given by the action that if we look at the state here S, which is state 1, we look at the first column here, then we take the action that has the largest value of Q. And now in this case, where we have started, so we have put zeros everywhere, then both actions are equally good. So we just take one at random. And I mean, going to the left, it doesn't really matter. We will just get back here. So we wait until we randomly go to the right. And then we interact with the environment, and that is to move to state 2. And then we get the reward. So that was a -1 because we spent energy swimming against the flow. And now we learned something. So we got a reward of -1 while moving from state 1 to state 2 by going to the right. So then we update the Q table using this new information. So we put Q at the current or old state as equal to 1 and taking the action right. So that's here, and put it to the current reward, which was -1. So that's one loop on this scheme. And then we continue on the next. So now we are at state 2. and now the agent should take an action. So we should take the largest, the action corresponding to the largest Q value, but now state 2 we haven't explored yet, so we can take these two by 50%. And let's say we took left by chance, and then we interact with the environment. We move back to the first state. We get a reward of 0, so we didn't put any penalty to move to the left. And now we see that now when we are in state 1 and take the highest Q value, we will always move to the left, so we will never do anything. So the scheme gets stuck at state 1, and we will never leave state 1 by following this scheme. So to be able to escape this state, we need to add exploration. So that means that instead of always choosing the greedy action, that is the one we currently think is the best one, we choose a random action with a small probability epsilon. So that means that when we are at state 1 and with a small probability epsilon choose a random action, we can go to the right, and then we get the -1 reward, and we get to state 2. And now we are in state 2 again, and maybe now we have the 50%, and maybe we by chance move to the right. We get the reward -1. And now we are finally in state 3. And then in state 3, we have 50%. Let's say we go to the right, and then we get the high reward from reaching the region with much nutrients. And then we get the high reward in the Q table here. So, and terminal 4 is state 4 is terminal, so we will not do anything more once we have reached state 4. Okay, so by adding exploration, we can reach all states, but still this is not a good strategy because in state 1 and state 2, according to the Q table, the best is to move to the left. So we need to have this epsilon greedy to be able to move to the right. So this is not a very good strategy. So somehow we need to update the Q in a better way to learn that we had a good state up here to be able to swim to the right in the state 1 and 2. And this is done by changing the update rules. Instead of just giving the reward, we give the reward plus what we expect the reward to be in the next state. So we take the current reward and then we add what we expect the reward to be in the future from the next state that we know. So this means that if we are at state 2, say, and move to state 3, then so we moved from state 2 to state 3 to the right, and we got the reward of -1. That means that we have -1 here, but then we need to add the Q value of the next state, which is 3, and the best action at state 3, which is 10. So we add a -1 plus 10, so that's 9. And then if we get to a situation where we move from 1 to S2 prime, we get the current reward, which is -1, and then we add what we believe is the value of the next state, which is 9. So we get -1 plus 9, which is 8. So by doing this scheme, then we get finally a policy that will take you to the nutrients by always moving to the right. So the Q table gives a successful strategy, and we can note that we learned the behavior by first finding something good, and then we propagate this good information to close by states, and in the end we find a strategy that moves to the target region. Okay, so this was a very simple example of a navigation problem, and another slightly more complicated problem is Zermelo's problem, which is a point-to-point navigation. So if we have a copper pod here, we move in a 2D turbulent flow to some region B. So it's essentially the same problem as before, but now we are in a 2D turbulent flow. And we assume that we have a constant swimming speed, so we just swim in our instantaneous direction with a constant speed. And the question is, how should we choose the swimming direction? And the naive approach perhaps is if we are at A and want to go to B, we always swim in the direction of B. So we swim always turning towards B, and we will get some deviations due to the flow, but essentially we move from A to B in a straight line if we can swim fast enough. But now if we have a smaller swimming speed, so this is compared to the flow velocity or the maximum flow velocity. So when we have a swimming speed that's comparable to the maximum flow velocity, then we can ignore the flow. But if it's smaller, then we tend to get stuck at fixed point or limit cycles. So we can't just move towards the target because we get stuck in traps. So that's where the reinforcement learning can be helpful. So in this case, we participate the 2D space in a number of cells. So similar to the 1D states before, we have 25 cells. And we assume that we can have 8 different swimming directions. And then we get negative rewards for state updates. So that's essentially giving a penalty as time goes. So waiting a long time to reach a target will give a large penalty. So we want to reach a target as quick as possible. And we also give a large penalty for crossing the boundaries of the flow or of the flow domain. And then we get a positive reward for moving towards the target and a large reward for reaching the target. So, and now one important difference from what we had before is that in the previous case, when we took an action, the outcome was always deterministic. So we always had the same outcome from taking an action. But now if we are in this cell, for example, and enter it here and want to move to the left, for example, or have the swimming speed to the left, maybe we move like this and move to this cell. But maybe if we start here and move to the left, maybe we go down, follow the flow and move into this cell instead. So the outcome of taking an action here is not deterministic, so it's rather stochastic. So we can go to different regions depending on where we are in the flow when we enter the different states. So therefore, we don't want to add the entire information of the new what we learned just recently, because that will destroy whatever we learned earlier. So therefore, we introduce this learning rate. So when this is 1, then we just have this first term. So that's what we had before. But now if we put a smaller number, 0.1, say, then we will keep 0.9 of what we learned before, and then just add the new information with a smaller weight. So this is something we need to do when we have a stochastic transition between states. Okay, so following this scheme, we can evaluate the trajectory, and initially we just move around randomly, essentially, and we get some information of what seems to be good directions at different states, but nothing definite. And we continue moving around randomly like this, and then eventually we have a trajectory that reaches the target, and that gets a large bonus. So that's a high Q value here. But the next trajectory, I mean, it still follows whatever information it had down here, so it doesn't know about this large reward yet. So it continues to explore around previous trajectories, but then eventually we get another trajectory that reaches the target, and as we move on, we will get more and more trajectories reaching the target, and we can see that the information that this is a good state builds out from that state similar to what we had before. So the information this is good builds out to the previous states or nearby states, and eventually we find a strategy that more or less every time moves to the target. So I guess two key points here. We had this information moving from the final state to the initial state. So that's one key point. And another key point is that we can look at the trajectories that we have explored here, and we see that some regions of the flow we haven't even visited. So Q-learning, it explores around trajectories that it currently thinks is good. But I mean, you would need so I mean, that's the strength of Q-learning, because the number of possibilities are extremely high. So we have 8 actions and 25 states. So that's 8 to the power 25 possibilities of strategies. So there's no way we could brute force and evaluate all strategies. So what Q-learning does is that it evaluates strategies that lie close to earlier strategies that we think are good. And in this way, we can continuously improve the strategy. And in principle, if we wait long enough or take time to infinity and a number of explorations to infinity, and if the system happen to Markovian, then one can show that one indeed reaches the optimal strategy. But otherwise, we will typically reach something called a suboptimal strategy or a quasi-optimal strategy. So it's something that's very good, but usually not the perfectly optimal strategy.
Kristian?
Okay. Yes.
Quick question about this. So
Yes.
this is really interesting. I was wondering if I remember rightly from my bachelor's physics that I had there. These turbulences tend to be extremely sensitive to perturbations, these turbulence systems. Is there a feedback of our swimmer back to the environment? Does the swimmer influence the turbulences as well, or is this passive? So can the
Yes, so we assume a one-way coupling. So there's no feedback from the swimming on the turbulence, and this is a reasonable approximation because these swimmers are very small. So they are smaller than the smallest length scale of turbulence.
Okay.
But I mean, if you have many swimmers, this will be an issue for certainly.
Okay.
But we neglect this problem.
Okay, cool. Thanks.
Okay. So essentially, I'm running quite out of time. So I can just briefly mention the kind of projects that we have looked at, and then maybe we can discuss after. So another example, a little more important for plankton navigation, or I mean, the previous example was important as well, but we had this diel vertical migration I discussed in the beginning, where the plankton needs to go to the depths during the day to avoid fishes. And the question is how this can be done efficiently, and that's the starting point of our studies on using reinforcement learning. So we had a simple vortex flow, and then before training, the smart strategy moves just randomly, just as the naive one. So the naive one is to always try to swim upwards, while after training we get a strategy that efficiently move upwards, and it does this by following a strategy that occasionally takes suboptimal actions. So sometimes you swim downwards in order to move upwards. So we were able to solve the navigation problem in a simple vortex flow. So that was the starting point of our studies, and then we have improved by looking at more realistic situations. So, for example, we have a flow model for turbulence. I will maybe not go into the details on this model. So it's something that we have been working on a lot. I have been working with Bernard Mielich a lot about these flow models. And the advantage is that if you want to do real numerical simulations of turbulence, it will consume all, it will take very long time. So the reinforcement learning, you want to do trial and error and do everything very quickly, and then it's beneficial to have a model like we use. So I will not go into the details on the model. And then we can find different strategies for swimming vertically. So for example, we found that if you look at the slip velocity of a settling plankton, you have the difference between the flow velocity and the plankton velocity is minus the settling velocity minus the swimming velocity in its instantaneous direction. And then you project this on the direction of the antenna, and then you just get the settling velocity times p, and the settling velocity is essentially vertical, so this is basically proportional to pz. So by settling in turbulence, you can get some partial information about the orientation. So basically, if you are a swimmer with your swimming direction or head in this direction, and then antenna in this direction, then since all the hairs will point away from the settling direction, you can determine which direction gravity is. And now if we assume that the swimmer can steer around the q-axis, so that's the direction out of the plane from the antenna, then if we have a positive pz, so that corresponds to the p direction like this, so then n must be essentially to the left, and then we want to steer clockwise to be turn it up. While if the pz component is negative, then p instead points mainly downwards, and then we want to swim in the opposite counterclockwise direction to swim up. And then in between there is some regime where, I mean, when it's when the p direction is more or less aligned with the z, we cannot sense any information about that direction, and we can't do anything. So we just take a zero steering velocity, and then one can convince yourself that this is also the optimal strategy in 3D, but I will not go into the details. But what one finds is that such a strategy, so this is based on local signals in contrast to what we had before. So this is something you can measure in the frame of reference of the swimmer, and we find that it performs fairly well. So the vertical velocity, the velocity going up compared to the swimming speed of the plankton is, it's not unity, but it's comparable to the swim velocity would have without the flow. So without the flow, you would have a unit here. You have something reduced velocity, but it's reasonably large. And one can note that the settling velocity, even though it takes the particle moving down, so the particle settles, it falls due to gravity, but the settling makes it able to sense its direction. So the settling allows it to determine which direction to turn to swim upwards. So if you would turn off the settling, you would get a zero velocity here. So without the settling, you would not be able to swim upwards. So even though the settling takes you down, it helps you swim upwards by giving information about the orientation of the swimmer. And then I had another example of this predator avoidance in still fluids. And the problem is that in turbulence, so you want to sense the fish larva on a distance, and the question is, in turbulence, the background flow will mask the predators. So to be able to escape the predators, you need to navigate to the low strain regions, and the question is, how can this be achieved? And well, maybe I will not have time to go into the details, but we can find an efficient strategy for doing this. So essentially, one finds a gradient descent of the strain. So by sensing the strain gradients on the different orientations or different directions of the swimmer, it's possible to determine the direction to swim or to turn to be able to move to low strain regions. And this is an evaluation of the strategy. So this is a 3D flow. So we have X, no, Y, X, and Z. And we have different slices in the flow, and we see that the plankton concentration is high in regions of low strain. And we also see that if we blow up one of these regions, plankton mainly a line against the flow. So this turns out to be a mechanism for counter-current swimming, which is something that was is observed in plankton in nature. Okay, so I went through these last steps quite quickly because we don't have so much time. But in summary, plankton navigation is poorly understood. So there are lots of navigation observations, but very little is understood. What are the signals they sense and what is the purpose? And most existing models use simple rules and basically so swim in its instantaneous direction, and then you get moved by turbulence, but you don't really respond to the signals of the underlying flow. So that's why we looked at reinforcement learning to find sensory-based navigation strategies. And these can inform new experiments to help try to identify what the microswimmers or plankton do in nature, and we can make better models. And in the future, the aim is to develop simple, robust strategies for artificial microswimmers, which has endless applications, as I described in the introduction. Okay, so thank you for listening, and here are some references that are relevant to this work.